designing software that can work with these different items transparently. The goal we have in here is to have a software that can control CPUs, GPUs, FPGAs, or even quantum computers. We are not there yet. Particular, for instance, quantum computers don't work even alone. So, and every time you combine something, you need to make hybrid algorithms. You need to optimize lots of things. But just to give you an idea, for instance, one of my students, Noelia Sanchez Gomez, made this repo, which is a nice resource if you want to learn a bit of HPC and optimization. It's a tutorial on optimize the QSIM library, a Google library to do simulations in a cluster. And you can read here how to install something like this, how to use profilers to measure how your code is working. And she measured, for instance, the cluster that we have now, one single epic node with 1.5 terabyte of memory can simulate up to 37 random quantum circuits, 37 qubits for random quantum circuits that are deep. Before we started optimizing the cluster, people were not getting before over 20. To optimize this, we are using libraries that are optimized. The IP is in Python. Then there is a C++ layer which is optimized using things like OpenMP, Pragma, OpenBLAS. I don't know if you know about HPC, but I teach and I can give courses like this. And this is a picture that shows how complicated it is to actually decide what is better. Like here we're doing brute force matrix multiplication of a deep circuit. And she's comparing the performance, the cost in a GPU, which is very good. It's an NVIDIA A100 with 80 gigas, and a last generation supernode. Using all of the cores, the code was optimized to use the cluster. Like she optimized the number of threads, the size of the blocks, the renormalization tricks to use perfect use of the L3 cache and the slash memories, and then we compare what is better, a single node using all of the cores, or the GPU, and surprisingly you get that, well, actually no one is better. It depends. For small system sizes, the CPU, which is this one, is much faster, but the GPU requires loading the data, and that takes a lot of time. So it's not worth to load the data until you pass above system sizes of 22, and then up to 33, the GPU is faster than a CPU, although these are not parallelizable problems. These circuits are deep, entangled, not really parallelizable. I did. Then the GPU has to think, you run out of memory here, so you need to use the CPU, but also this exponential is going to cross the other one. So at some point, the CPUs become better again. And then after lots of optimizations, we concluded, well, you have to basically test your thing and your algorithm to know how to do the best split of resources. And there is another nice plot in here, which is how the efficiency scales with the number of threads. If you parallelize the matrix multiplication, Elia showed that you can use all of the cores of the cluster and it doesn't get worse. This is actually not typical in a high performance problem. Typically, you introduce more threads and you have an advantage, but problems that are hard to parallelize sometimes get negative rendimientos, negative improvements if you add too many threads, because communication scales up and you run out of memory also. But then here, this software, you can see that matrix multiplication of deep entangled circuits can be parallelized a lot. We use up to 96 cores. The performance doesn't get worse, although it saturates at some point. It's not actually so worth to go to use all of the cores. Another thing we do is related to classical simulations with other methods that are not brute force. Here we have, the complexity of circuits is measured usually with the number of qubits, the size, which is the number of gates, and the depth. There are different types of simulations. Probabilistic, you sample from the distribution of the wave function, you compute coefficients or expectation values. These are deterministic. We study all of these, but I wanted to tell you that there are different types, and each of them is studied for different reasons. Some of them are useful to compare quantum and classical algorithms. Others are useful for complexity theoretic studies. One of the things we can simulate is Clifford circuits. Clifford circuits appear in quantum error correction, so you have a fault-tolerant machine. You can pretty much guess they're going to appear in there. And you compile circuits that are universal in terms of Clifford and non-Cliffords. One of the schemes that people use in fault-tolerant quantum computing is called magic state distillation. which uses teleportation of states and operations that are Clifford, which are these ones, C-nodes, control sets, Hadamard, phase gates, Pauli measurements, to do other gates, like the set of the fourth root of the set gate, which is called the T gate. That is not a non-Clifford gate. The simulation algorithms that we have in here use something called stabilizer formalism. Now, the funny thing is, these gates that appear in quantum error correction are simulable efficiently, but they are highly entangling. They generate non-locality. They can do things like teleportation, and they are able of creating topologically ordered states and doing lots of things. It's actually not so clear why they're actually not universal. So that's a topic of study. We have studied in our foundational projects connections between the circuits and Wigner negativity and non-contextuality. Like one thing we do is developing models for these circuits that are classical and identifying that there are sometimes classical features in them. The main technique people use to simulate is called the stabilizer formalism, which we studied in the master in the quantum computing course. But the main idea was to represent states as eigenvector of matrices, and you keep the matrices stored instead of the vector and the eigenvalues. And the matrices are Pauli, x, 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 z, z, z. When you have a Clifford circuit, and the stabilizer state stabilized by the stabilizer operators, the matrix description evolved under the unitary gate has a property that these Clifford gates map Pauli operations to Pauli operations. Because Paulis they always are Paulis after the action of the gate. There is an algorithm that tracks that and officially simulates the circuits. Also uses linear algebra and several tricks in there. Now, this is classically simulable, but also you can extend these methods to simulate arbitrary circuits. The cost goes with the number of non-Clifford elements, and actually that's something we're doing in the group. So just to show you a current paper, for instance, we have right now so one trick that you use to generalize this, and you also use this as something similar in tensor networks, is to split something that is hard to simulate as a sum of things that are easy to simulate, like a unitary as a vector of Clifford unitaries, and then you minimize the one norm. If you do that, you can decompose a hard to simulate circuit as a sum of circuits, and there is a sampling trick you can do there to now decompose this into many easy to simulate circuits. You can use this for many things, for classical simulations or for distributing resources in distributed computing. Imagine you have a heterogeneous system with quantum processing units and classical ones of different types. You can use decompositions like this and mathematical methods to divide the work in an optimal way, like parallelize in the best way. This is something we can do in many ways. One way is to do it in the stabilizer formalism, which is like Cliffords versus non-Cliffords. But we can apply the same tricks to tensor networks. You'll take things that are not entangling, and you decompose them in terms of non-entangling things. Objects. You can do this in a coherent picture using unitaries, or you can also work in a channel picture, pure state picture, density matrix picture. This gives gives different methods. Like IBM circuit knitting is an approach which is of this kind, but they work in the channel picture, and they use non-entangling ansatz to decompose, and this is used to distribute resources across different machines. These problems are very difficult because in order to use these methods, you need to do a super expensive decomposition of a matrix or object, and this is typically a very expensive convex problem. And a nice thing here is that this can be pre-computed before doing the simulation, but it's very, very hard. And in this paper, my postdocs, for instance, we are working on optimizing these methods. So the thing they do here is, this is the plot I want to show you. It's recent. We haven't published this yet. This is like a new algorithm that exploits symmetries of the gates and algebraic structure, linear dependencies, everything that is redundant to reduce the dimension of the problem. We have applied things like this. We identify in typical non-Clifford gates symmetries, and we are able to improve the algorithm of the decomposition doing symmetry reductions. So these are numbers they are getting for improved decompositions. This here, what you have in here is the extent of control rotations. The thing is, we go above typical system sizes, and the trick there is to realize that these are diagonal and some of them are real gates, which are symmetric. I'm going to finish here, but if you want to discuss later, I also have more projects, one on tensors. And I have a student, Antonio Jesus, who is doing MPS simulations. Like he's using, it's another common technique to simulate, to decompose things as tensors. And here, the cost goes with the entanglement of the state. The MPS is a representation that looks like this. You represent states as products of small tensors. And it's a numerical method that you can use to simulate circuits that are not very entangling. He also implemented this in the cluster, and we are getting this thing over here. Like this is a plot. Like when you can see here, when you have circuits that are not very deep, you can scale the number of qubits massively. Like, I don't know, you restrict the depth to be 9 layers, 10 layers, 11 layers. You can simulate circuits of up to 60 qubits in a cluster, and not so much. But however, if you increase the depth, you can see that it blows up quickly. Like this is the color graph, number of qubits, layers, and this is going exponentially up with the depth. Yeah, I think I want to say more there. He's implementing this in using iTensor. We have I wanted to mention these two projects because we have a poster of 2 students here. We have Boaz, is going to be talking about the decompositions problem in his poster, and Rocio, who is also there, is going to talk about the tensors. And if you want to learn more about that, you can go to their posters later. With this, I would like to thank you very much.
Thank you, Juani, for your very nice talk. Is there any questions?
So, hi, Juani. I am Rocio. At what point do classical simulation become impractical for simulating quantum systems? No? So, at what point do classical simulation become impractical for simulating quantum systems?
Sorry. Okay, the numbers vary a lot from the method and the type of circuit. I think the best thing to talk here is to fix an algorithm. Like we're talking about random quantum circuits that are deep. I think the simulations, depending on the cluster, are very difficult above 45 if you are poor, like most people here. Like here's the thing, imagine you only have one single node, epic node, last generation, you run out of RAM about around 40. So then you have to combine supernodes. But combining supernodes is more expensive, and then you need to, you want to go to 70. I mean, there are simulations where people have done more, like depending on what, but you can go higher, but it becomes more complicated. I think in that case, for instance, it's very hard to go to 70. Like, just a lot of work.
Hi. You say that you compare the use of CPU and GPU. So is there a way to combine both of them so you have a more efficient way to simulate?
Yes, actually, that's what Noelia has to do now. They're starting the PhD. Then first, we are comparing single device against single device very well, and then the next step is to combine two. And you can actually, the library allows, several libraries allow to do this. not all libraries, which is there is another huge problem here, is to have good software that works well with many multiple things. It's not easy. So it's actually becoming more important to have good quantum software engineers and architects, because if you want to have a library that works on several things at the same time, it's a lot, and for one single researcher. So the best is to make modular software so that specialist does a part and another specialist does a part. That's what I'm doing with my PhDs at the moment, trying to make a good library for doing a simulation across different devices.
Yeah. So, well, first, thank you for the presentation. The question was related about the MPS simulations, about a little bit about the results. Basically, the question is, yeah, over there. You are measuring also, the number of layers, the number of qubits, and the time. My question is about the precision. Like when you perform the MPS, you have a bound dimension. Obviously, you are not performing exactly. So I don't know, like.
Wait.
Maybe you can use this one.
Typically, tensor networks use point precision. Like you can just basically choose between long double or double, but in other cases, exponential precision. So they are very precise compared to, I don't know, if you do estimation procedures like Monte Carlo estimation, the precision is 1/poly, but in a tensor network contraction, it's 1/2 exponential. And in the MPS there is also an error, which is that when you in the PS representation, you can truncate to reduce the bond dimension using something called time evolving block decimation. And I don't know you're talking about that, but that doesn't work very well if the circuit is deep. I mean, like very soon you cannot do truncation if the circuit becomes deep. Like that's this thing. You decompose the tensor into singular values with a singular value decomposition. You can remove some of the bond the dimension a bit. You get a larger error. You can calculate it. The error is bad if the circuit is deep. So in the end, if it's deep, you don't do it because the error is just too bad.
Okay, any last quick question?
Thank you, and thank you for the talk. You mentioned very early in the slides that there are many different quantum resources that are closer. Okay. You mentioned at the beginning of the talk that there are some quantum resources that are known to be related to quantum advantage, but is there a favorite, or is there some other quantum resource that is going to be considered necessary?
Some people have a favorite. In my case, I am trying to prove that contextuality is not a resource because I hate it, but I am not being lucky. I'm getting positive results.
Okay.
Which is my please don't cite one more side effect. It's wrong, but I cannot prove it. No, actually, it's not it's complex. I think right now we don't have a clear resource that is good for everything. It's very insufficient. But I mentioned several of the most important ones, and I think people need to look into more, like, I don't know, scienticity and things from ontological models. There is more work to be done in that area.
Okay. That's all for me.
Have time for one last. Do you want to ask a last question?
Hello. Thank you for the talk. It was very nice. I wanted to ask more in the political side of things, given that like the amount of the things that you show in the talk, like the amount of resources that it takes, like the ethical issues or like the arms race for quantum technologies, do you think that it's, and the fact that now quantum computers are not really, as you said, so good, do you think it's even worth it right now to spend like so much money in buying like computers from IBM or whatever this pursuit for it?
Actually, it's a complex question. Where are you from?
Brazil.
Yeah. So right now, the United States is colonizing us with algorithms in the sense that they are trying to become the primary all of our services make us depend on them. Like we all use Microsoft Office in administration. We all use Microsoft products. And they're trying to extend this to control us politically. Because if we, for instance, now they pressure us to go to war somewhere in the European Union, it's actually publicly said by them, like they count on us not being able to say no because they could seize the software access and then our economy collapses. So from one side, it's actually quite important to be software independent and that you have your own software and be careful to be independent of software companies from one single country that is becoming more and more and more aggressive. And I think actually this is what I'm earning. But in the case of quantum computers, I'm not sure the problem that we have is more important is this question. I think it's more. Now there is a web page called No Tech for Apartheid, made from Google workers and Amazon X workers and Amazon X workers, and they make a lot of reports on what's going on in the States. And they have good reports on this subject. I think actually it's a new thing to read. But yeah, I think the questions that worry me more about quantum computing are not that one. It's more how they get entailed in the whole picture of all of the big tech companies working. But I don't think we are independent from them. I think we're just a part of them, and very small.
Thank you.
I think we should use Linux.
Okay, then let's thank Juani again. And now we have the coffee break.